Um, I'm working on a project that I found from the ML Safety Scholars Summer 2022 Final Project Resources, which I found through the ML Safety Scholars, this curriculum that I found somewhere online. The link is shown here, and the link to the project resources is shown here as well. So let me read through the details of the project. So we have option 6, MNIST project. That's the project that I'm working on. MNIST is a dataset for handwritten digit recognition that is often used in ML. It's available as part of the standard datasets of nearly every ML package, and you can find and adapt many MNIST classifier projects online. For example, here is a collab with a basic MNIST classifier. You are welcome to use this code exactly as a starting point. So I have this collab project here that I found, and actually, so this one's the original, but I made some modifications to it, which I have at this file here. This project isn't to build an MNIST classifier, but an MNIST classifier that satisfies as many desirable properties as possible. The task is to create a classifier that has as many of the following properties as possible. Robust to adversarial attacks. This includes LP norm attacks, L0, L1, L2, and L infinity attacks. So I will be clear before I go ahead that I'm not very familiar with what these attacks or what these properties really mean. But I hope that the process of me doing this video, which in itself is sort of a step for me to become more aware of the way that I think, I am hopeful that I'll be able to deepen my understanding of these properties. Robust to distributional shift. MNIST-C contains MNIST-type digits with various corruptions applied and can be used to develop your solution. Can be used for anomaly detection. You can use fashion MNIST or not MNIST as examples of anomalies. High accuracy, so the standard MNIST classification problem. Low RMS calibration error. In other words, model predictions are well calibrated. Error detection. The ability to recognize in which cases the model is most likely wrong. To do this, you may want to experiment with the data augmentation techniques, such as mix-up, cutout, noises, pix-mix, salt and pepper, and outlier exposure. You may also want to make use of the lost MNIST digits, a set of MNIST digits that weren't included in the original dataset. Be sure to use proper machine learning best practices, such as using a separate validation set to experiment with different approaches, and holding out a third test set for testing final models. You should start with a literature review. Implementing ideas from past papers is fine, though note we aren't aware of past papers that tried to satisfy many of the properties above at once. Here is a good paper to start off with for adversarial robustness. So our goal is a deliverable, which is to write a final 2-page report discussing the strategies that you tried and how well they worked. And we also hope to submit a collab notebook with our code. So I think in the original iteration of this project, it was meant to take around 40 hours of work. And to be honest, I don't exactly know if I'll have enough of a sense of direction to pursue the full 40 hours. But I do hope that I will be able to learn some stuff, and I'll be able to sort of get, get closer to having something that, having a meaningful project here. So let me walk you through what I've done so far. So let me close Gemini for now. So I started out with this PyTorch with the MNIST dataset notebook that was already linked in the project directions. And what they gave to me is sort of, pre-prepared code, which is a basic MNIST classifier. So we have, installation statements to install the Torch Vision. And then we have some import statements here. Then we have our arguments being defined here, like our batch size, our test batch size, epochs, learning rate, momentum, seed, log interval, and CUDA. And then we run through we set out our training data. So actually, this is a bit of a modification from the original, but I separated out the training data. Um, I think that's referred to as a data set. I separated the training. So just to be clear, so this part that now corresponds to the training data variable was originally directly in the train loader line, so which replaces this particular part of the train loader line. And similarly, this part here, which I'm highlighting right now, was originally in place of test data in this part. So I felt that separating out the variables might make it a little bit more easy, a little bit easier for me to sort of digest the structure of this program, as a lot of it, quite frankly, is a bit kind of difficult to understand. So we have loading the data, and then we have the displaying of the images and the labels here. And so I think I actually built this particular part here. Let me just take a look here for a minute. Yeah, so I built this part, or I copied and pasted this part from I can't remember where I got it from. I think from Torch Vision, from PyTorch documentation on data loaders, in order to sort of visualize like elements of our data set. So this part here is just intended to, it's intended to get our train features and train labels based on based on making train loader an iterator, and then we print the feature batch shape. We print the labels batch shape. Then we squeeze the image. So honestly, it's kind of hard to understand what's actually going on here, but we have a squeezing of image, and then we have the label here, and then we use this part corresponds to matplotlib, and we're using matplotlib to essentially show the contents of the image. So we have here that this particular figure, this particular image, corresponds to an 8 in our training set. And this part was given in advance. It defines the structure of the neural network. So we see here we have, okay, I'm going to do my best to run through it. Not exactly sure if my understanding is correct here, but first of all, we have a convolution being defined here in conv1 and conv2, and then we have a dropout line, and then we have a fully connected neural network, linear, and then we have a second fully connected neural network. And in our forward step, we have a convolution, and then we're doing a pooling layer, and we're using a ReLU activation. Similarly, so that results in the variable x, and that variable x is then used for the next line, which uses a convolution, a dropout step, a pooling layer, and an activation, and it adjusts the dimensions that we use for our x. Then we have a fully connected layer being applied to x, and then we use our ReLU activation. Then we have a dropout step with training as self.training. I don't exactly know what the purpose of this is, and then we have another fully connected layer, and there is no activation for this part, I think. And then finally, we get probabilities for softmax. And then we have our training step. This takes in an epoch, and this is model.train. Don't really know what that means, to be frank with you. I think this is running the train method of the I think that runs the train method of the model, which is okay, train method of the model. So I think that refers to, so later on when we have model equals net, we define the model variable, and that's going to be, the train model is going to be run on that. Oh, I think because we have net, because net is like a superclass, or n dot module is a superclass of net. The train method is already predefined from what I understand. Then we run through the batch IDXs, the data and the target, and then we have if args CUDA data target is equal to data.CUDA target.CUDA. Data target equals variable of data and variable of target. This part here is meant to zero out the gradients for this batch. Now we're calculating the loss with a negative log likelihood loss, which is useful to train a classification problem with C classes. And then we calculate the backward gradients, and then we do a one-step update on our parameter. And then now we are printing out the loss periodically. So here, I noted this here, but this part here, loss.data, was originally loss.data at index 0. And I modified that to loss.data because I think when I tried using loss.data at index 0, it did not work. I think that may be attributed to maybe this being from a prior, or using a prior PyTorch version, so I needed to make alterations to make it work. And then we have the test function here. And so basically in this step, we go through our test loader and we get the data and the target. And so we have our output, which is based on model of data, model taking in data as an input. And then now I think we use a NLL loss. What does that mean? So NLL loss corresponds to negative log likelihood loss. Okay, so we add to the test loss the negative log likelihood loss based on the output given by the model taking in the data, as well as the target. And then size average equals false. So we have size average. So size average, that seems to be deprecated, but it refers to the fact that by default the losses are averaged over each loss element in the batch. Note that for some losses there are multiple elements per sample. If the field size average is set to false, the losses are instead summed for each mini batch. Okay, so it's not exactly clear to me what that exactly means, to be honest with you, but I think that so when we set that to true, it means that we're going to average the loss over all the elements in the loss. But so like we have an average, like dividing by the number of elements in our batch. But if we were to instead set that to false, then we would just get a sum for each mini batch. So we're actually, I think that means that we are actually going to be adding the loss, like summing up the loss for the entire batch without dividing by the number of elements in our batch. And here we have pred equals output.data.max, index 1. So here we're going to get the index of the maximum log probability. And then we have correct plus equals this part, which is not exactly clear to me what that means, but we end up getting a test loss, and we're dividing that by the number of elements in our test loader dataset. Okay, so I think here we're getting an average loss in the number of the accuracy, which is represented as 100 times the correct number, like a number of correct items classified, divided by the number of elements in our test loader dataset. And so here's where we actually do the testing, the training and the testing. And I wrote here a little bit about my objective, which is to incorporate a number of techniques for data augmentation to see if it's possible for me to improve the results, the accuracy of the model, and furthermore, I compare the training and testing loss to detect overfitting. So let me just take a look back at this particular line here. So I'm pretty sure I got this from somewhere on the internet. Okay, so I think it's probably from this article. So um, so I tried to visualize the data set, and it may have been from this article, I think. Okay, okay, so I have iterate through the data loader. So the the code for this part was adapted from this website, which I will copy a link to and paste that in here so for everyone's reference. Okay, so now I want to think about the direction that I want to pursue for the data augmentation. So some of the steps that were proposed in the project guidelines were things like looking at mix-up, cutout, noises, pix mix, salt and pepper, and outlier exposure. And so honestly, I don't really, it's kind of hard for me to understand, like, I guess, what's actually going on here. And so just to sort of refine my understanding, um, I would actually like to take a look by first starting off with this particular paper that was recommended for adversarial robustness. And I'm just going to try to do a read through. Obviously, it's very long. Well, it's not that long. I guess the real meat of the article goes up to like page 9. But I'm going to go ahead and read through this article and try to sort of understand sort of if I can get any sort of inspiration from this.